Hi, this is the third of the COMSOL videos that I've prepared for Bioengineering 167, Medical Diagnostics. In this one, we're going to combine everything we saw in the first two videos and revisit our model binding-based biosensor, but this time we'll give it a full treatment that combines both diffusion and convection in transporting target to the sensor where it is bound and ultimately detected. So we are already connected to the VPN in this example here, so I'm going to run COMSOL. So this time we're going to do another 2D simulation, and we'll combine the two physics modules that we've been using up to this point, laminar flow and transport of dilute species. Okay, here we go. So there's our model wizard 2D. I'm going to grab them here from recently used because I'll show you where they live in case they aren't appearing there for you. Under fluid flow, under single phase flow, we have laminar flow. I'll add that. And then I will add transport of dilute species, which lives under chemical species transport. And that's that. Very good. All right, so on to study. And just like last time, this is going to be a stationary study because the variables aren't going to change over time, so we don't need to use a time-dependent one. Okay, so that's done. Here's our default screen. So I'm going to switch the units to millimeters, zoom out a little bit to see a few millimeters worth of space, and then I'm going to reconstruct basically the same binding-based biosensor that we made in the first of these three videos. I made that out of three rectangles. The first one here will define the boundary right there where the actual sensor will be located. Remember, this is a sensor that we're assuming has perfect binding. If the target solute molecule ever bumps into that surface there on the bottom of the square, we assume it's trapped and trapped forever, and that's how we'll measure it. And then I'm going to draw a few more rectangles like U and U, and use those to define a little bit of the region of the channel leading up to or beyond the surface of the sensor, but my sensor is located right there. Okay, so let's zoom to the extents there. We can see the boundary that will become the sensor surface eventually. And so the next step is to assign a material to it. I'll right-click here and select Add Material from the library. As usual, I'll just use water for simplicity here, but you can create your own materials if you'd rather use blood or something else that's more biologically relevant. In a moment, those all turn blue, indicating that the material has been assigned to those domains. Very good. Okay, so the usual process here under laminar flow, we have our fluid properties initialized, being inherited from the material, which is correct. Our initial values are no flow within this, which is good. We're going to add flow, and we're going to create an inlet here and an outlet here, the same way that we did in the previous video. But for now, our default boundary conditions are all walls, which is good. Under transport of dilute species, our transport properties here, they remember from last time, the key thing that we must change, the velocity field under the convection tab here must not be a constant user-defined field. We must switch that to the velocity field that was calculated in the previous step. So make sure we do that. Otherwise, the results will not make sense. The initial boundary conditions are no flux throughout all the boundaries, which makes sense. The solute is initially neither coming in nor going out. And the initial values of the solute throughout are 0. Now, in our first video, we changed this concentration to represent an initial starting concentration, and then we did a time-dependent simulation. In this case, we don't need to use this. We're going to keep the initial values at 0, and we're going to send our fresh solute into this through an inflow located on this inlet shown here. Okay? So I can now actually simulate this. So I'm going to build the mesh first and see what we have in store. And so by virtue of combining laminar flow with transport dilute species, it's giving me a much finer mesh than I got in the first video by default, where I just had diffusion at play. And so at this point, I should be able to compute my simulation and confirm that everything is working. I don't expect it to be interesting at this point, but I expect it to work. And indeed, that's the case. Here are three plots that I get. The first one shows 0 velocity throughout the system, which is as expected. I haven't intentionally started anything flowing yet. There's no pressure drop in the system, and there's no concentration of my solute anywhere in the system because I haven't added any yet. So first things first, let's add flow to this system. I'll right-click on laminar flow and specify an inlet. On the left-hand side here, that's where my target, my blood, my urine, whatever will be flowing into this. For velocity, we can start and specify, say, a millimeter per second is just fine. And then I'm going to add in an outflow, or rather an outlet, over here. And the default condition of 0 pressure, 0 pascals of pressure is just fine. Okay, let's simulate this again to confirm that I haven't broken anything. Okay, good. So here I see the rainbow color of a laminar flow profile, the highest flow here in the middle of our channel, the lowest flow over there, and a parabolic distribution of flow rates going laterally across the channel. Interesting little phenomena here because in the inlet here, we specified a normal inflow velocity. What COMSOL simulates then, if I switch back over to the velocity, it assumes that that 1 millimeter a second inflow velocity is applied along the entire channel width, from the edges all the way to the middle and the other edge. Now, of course, we know that in laminar flow conditions, that what we'd call plug flow there will quickly develop into a parabolic flow, and this distance over the distance from here to about there shows the distance over which it takes for that flow to develop properly. So everything from here on over makes total sense in a laminar flow context. Okay, good. So my flow appears to be working. So now I can go back to transport of dilute species and add in my inflow. So showing the concentration of glucose in the blood or whatever that's flowing into my system here. Here I can specify the concentration. I'll again say 1 mole per cubic meter or 1 millimolar. And then of course I also have to add in an outflow over here so that the solute that's not captured on my sensor here has the opportunity to flow out if need be. And then finally, I'm going to add, just like I did in the first video, under surface reactions, a fast irreversible surface reaction on my sensor surface, which you remember is this highlighted boundary there. And then I'll use again a -1 stoichiometric coefficient, telling COMSOL to represent binding, not delivery. The negative sign here means that the solute molecules will be going from inside the system outside, or a negative flux in COMSOL's sign convention, and the 1 just specifies the stoichiometry of the binding reaction. The default of 1 is just fine. Okay, so down to the study, and we'll click compute again and we'll see what we get. Okay, that's the velocity picture again. You know, the velocity view is not going to change any, and so to keep us from looking at it every time that it comes up, I'm going to delete that plot, and I'm also going to delete the pressure one, because those just aren't interesting for this simulation. And that will leave us with the concentration. And that's what we see here. So you remember last time in the first video we saw something similar to this, a planar depletion zone, where if we zoom in, there was a little plane, a little thin layer of blue here, representing the region of our sample that had had its target depleted from it. So we see something sort of similar to it, but you can also see the asymmetry that the flow from left to right is causing. We see fresh red material, fresh unbound target flowing in from the left. Some of it, particularly the part of it that's in the vicinity of the sensor here, might get transported by diffusion laterally to the sensor surface and be captured. That depletes the target in this region here. But most of it, you can see up here, is not being bound. So with this particular combination of flow rates and diffusion constants and whatnot, we're not capturing very much of the target that's going into this system. But we see that we are having some effect on it. And downstream of the sensor, you see these colors here indicating that this region of the flow has been depleted somewhat of its target. And so, so the sensor is working as we expected. Now I'm going to do a little trick here. I'm going to do 2 things to our plot here to make sure, first, to make sure that we're not being lied to, I will again manually set the color range to run from 0 to 1. This way, as we play with the different flow rates and things and change the concentrations in the system, COMSOL won't automatically rescale the color bar and make for confusing results. And then I'm also going to, under concentration here, add in, just like I did in the first video, a contour that lets us visualize the point at which the line, the concentration at which half of the target solute has been consumed. So here I am specifying the level of concentration that I want that to occur at, but interestingly, you notice that COMSOL in this case defaults to meters per second. It defaults to using the data from the fluid flow calculation, even though we're in a concentration plot, which is sort of amusing. Anyway, we have to change that, so get rid of the fluid flow entry there, and then under here I can go to component 1, transport of dilute species, species C, and then select C, the concentration. That's what I want, not the flow rate. And then when I select that and hit enter, or hit plot or whatever. There we go. That will update the units for me. I didn't have to change that. And now, happily, I can go down here and set my level again to be 0.5 moles per cubic meter, and that will set my the level of the line that will be drawing in that halfway point along the concentration gradient. And then also, so I can see that line a little bit more clearly, I'm going to change to a uniform color of the line, just like I did before, and I'll make it a black line. There. Okay, let's plot that. And there it is. It's hard to see on this scale. But that's the line. And so everything below and inside of that line, that fluid has been depleted of at least half of its target solute contents. Everything north or above it still has more than half of its contents. Okay. So now we got that working. What can we change? Well, there's lots to change, and over the rest of the course, we're going to explore the relationships between the sensor geometry, the sensor size, the channel height, the diffusivity, and other things here. But for this demo, the easiest and most interesting thing to change is the flow rate. So let's do that. You can imagine if I go to an even faster flow rate, I'm just going to make this thinner and thinner, right? Because I have more and more of the fresh target blasting past the sensor, and diffusion has less and less time to transport anything to this sensor here. So I'm not going to simulate going to faster speeds because it's sort of uninteresting. But instead, I'm going to make the flow slower and slower, and we'll see what effect that has on the behavior of our sensor. So that's done under inlet 1. So to make it slower, I'm going to add a 0 here to decrease the flow rate by an order of magnitude. And then I'm going to right-click on my study and simulate it again, and we'll see what effect that has. Okay, so if you remember what it looked like before, this is reminiscent of it, but I think that the depletion zone thickness here is growing. Now I see a slightly taller region here, and now a good third of the channel has been affected visibly, although still downstream of the sensor, all of the channel still has more than half of its starting concentration of the target, the red stuff present in it. But as we slow down the flow, more of the a larger fraction of the target that's flowing into the system from here is actually being captured onto our sensor here. A little less of it is reaching the outlet here. Okay, interesting. Let's decrease the flow rate by another order of magnitude. And we'll simulate it again. Okay, more of the same. There's a transition occurring that's kind of reminiscent of the transition that we saw in the first video when we had purely diffusive-based transport of target to our sensor. But here we see the region of depletion is no longer a thin plane on top of our sensor, but it's starting to blow up like a balloon. It's starting to turn into something a bit more radial shape here. And interestingly, right here you can see that the depletion zone is actually growing upstream. So this is showing us that we are finally reaching a slow enough flow. The convection, the flow from left to right here, is getting slow enough that, it's still winning relative to diffusion, but some lucky solute molecules are actually able to diffuse to the right so fast that they diffuse faster than they are flowing. And in that case, that means that they are sort of locally depleting the region upstream of our sensor. Just this little bit here, they're depleting it of our target molecules and causing a depletion shape that's actually starting to work its way upstream, interestingly. Of course, there's much more depletion downstream because that's the direction of fluid flow. But so anyway, we still see a fair bit of target here that's passing our sensor and not being captured. Let's change the flow rate by another order of magnitude, dropping it again. It's getting to be quite slow flow. And I'll right-click and run my computation again. Okay, and in the process of doing that, a major change happened. Now we see that the depletion zone, the line of 50% depletion, is no longer smeared out this way. Now it runs all the way from the bottom of the channel all the way to the top. So clearly we passed a major threshold there. And the threshold we passed is that instead of just consuming a fraction of the target molecules, the solute molecules that are coming in. Now, in this case, looking at the dark blue colors over here, our flow is so slow that convection is losing, diffusion is winning, and our slow transport of fresh target molecules here is being, if you will, beaten by the diffusive-based transport of the molecules to the sensor surface here where they are captured. And that's why this line is actually moving upstream, and we see the rainbow color scheme actually to the left of the sensor here. So now we, just like in sort of like in the first video, we've transitioned now into a regime where we have no longer a planar or a radial depletion zone, but now a linear depletion zone. Linear meaning that it's marching down the line of the channel to the left. So let's zoom out and look at the entire channel view here. And you can see now that we're still sending fresh red stuff into this channel, but the flow is so slow at this extremely slow flow rate that diffusion is given enough time for basically all of the solute molecules to be captured on our sensor surface here. So if you had an application in mind where you had a very precious, very rare solute present in your sample going into this sensor, and it was imperative for you to capture all or nearly all of those molecules in your biosensor, then this sort of regime might make sense to you. The downside of this is that we have such a slow flow at this point that the actual flux of molecules on this sensor, the number of molecules that we're capturing per unit time, is actually really low in this case. And having a higher flow rate might actually be advantageous if the flux is important. If the number of molecules per unit time being captured is crucial, then some of the earlier flow rates that you saw might be better. But at any rate, we've demonstrated here that by changing the flow rate, we pass a waypoint, a tipping point, past which we're no longer depleting just a region of the channel contents, we're now depleting the entire channel contents. And indeed, if I decrease the flow rate even further, might as well do one more, we'll see even more of the same behavior and more complete depletion of all of the solute molecules in our system, because now, yes, the flow and the transport of fresh solute molecules is so slow that our sensor, which is located here, is easily able to consume all of those solute molecules by random diffusional transport alone. Okay, so that's the third of the simulations that I'll show you. Hopefully this has been helpful to you and will be helpful while you're making your COMSOL projects for the class. Bye for now.